Greetings, welcome. So a couple videos ago, we tapped this out by hand. We'll do this again real quick, just to refresh you, that if you have a 9-volt battery like this, and the positive comes out here, and then it goes round through an inductor, and you have the negative of the cap connected to the negative, you complete the circuit by connecting the positive here. The cap charges the battery. So if we don't have an inductor in place, and let's get a meter on here. Not sure if they'll both fit on the camera, but we'll connecting it now, and it charges to 9.22. So that's what this battery's sitting at, because that's what it charged this cap to, 9.22 volts. So that was fun. Now we'll discharge this cap, and we'll run it through a conducting diode. So if I can make a good connection. Yeah, 1, 2, 3. And it doesn't go up to 9, it goes up to 15.2. So that's interesting. Now, with the conducting diode in there, it does look vaguely like a boost circuit. It's different than a boost circuit though, because whether the diode is in there, or if we're just going like that, we're just leaving the battery connected. You can't do that with a boost circuit. It would be a short across the inductor. So what if you wanted to make this into a boost circuit, you would take the conducting diode. I'm not going to do this right now, but you would take the conducting diode, leave it connected to there, and then you would tap, 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 tap. Short little pulses where you're shorting across this coil, and you wouldn't leave it connected, because then it would just have the resistance, it's only like a couple ohms there of this wire, the direct DC resistance. That would be a boost circuit. This is not a boost circuit. This is going in series out to here, and the similarity is with the conducting diode. And because of that difference between the boost circuit, you kind of run into another issue, don't you? So let's charge her up. 15. Now taking this off, let's do it again. Let's do it again. Boom, 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 boom. It's just draining out through there. So you only get one shot there, because you're not shorting the thing, it's just charging into the cap. So it's like, all right, well, that was fun, let's call it a day. So it's, what do you do then? So let's charge her up again. And now I'm just going to connect this briefly so it doesn't have time to leak out. Okay, so we're at 15 volts. Now what you can do is you flip the cap over, so let's do that. So I flip the cap over, we'll just check. Okay, we're at negative 14.9. I don't want it all to drain out. So now with this at negative 14, negative 15, and this at 9, you have nearly a 25 volt difference across here. So what's going to happen if you connect it across the connecting diode? Is it going to go to 0? Is it going to go to negative 3? Or is it going to do something different? So now we'll have to connect it after we make the connection. So we'll 25.6. So it doesn't do any of those. It goes from negative 15 to positive 25.6. So in the last video then, I noticed that I stumbled across nearly the same thing when I charged the cap through an inductor and then discharged the cap through a second inductor. So 2 inductors, and as we saw, once you dial in the timing of where the voltage is swinging with the 2 LC tanks, you get a voltage transformation of larger and larger positive and negative flow there. Although it did top out after about 8 to 10 fold transformation. In other words, from like 5 to 40 and nearly an 80 volt top to bottom, peak to peak swing there. And I think I understand why that's happening, but that'll get too far in the weeds for now. But let's return back to this one. What if we want to just create this with, one inductor and flipping the cap back and forth? So you can do a lot with Arduino Uno and a breadboard, but it's not going to physically flip this cap back and forth for us. How are we going to do that? To do that, we need to build a circuit that's called an H-bridge. So let's build electronic circuits. So let's look at what this person did. And an H-bridge is a simple, sometimes, that lets you control a DC motor to go backwards or forwards. So in other words, the current flows one way or the other way, which is exactly what we're looking for. So it's an H-bridge, and he shows an example of it here with transistors and diodes and resistors. And here's just sort of the idea with switches, and it's called H because you got boom, boom, and the load there, and that forms an H. And then when you actually start to build it with transistors, it starts to get a bit more complicated. And there's one example, but even that, it gets more complicated than that if you want to do it right. And you start having to worry about all of this stuff with transistors that I don't want to worry about, like base emitter voltages and things like that. But suffice it to say that it will run differently at different voltages. So you'll dial it in for one voltage. And for people that follow John Bedini, I'll show you. It's called the Bedini-Cole bipolar commutation circuit. So the same idea of switching from positive to negative, he and Ron Cole used to drive in their case it was a setup called a window motor, but where you have a a north-facing magnet coming by, and then a south-facing, then a north-facing, then a south-facing. And so you need to switch the current in your inductor back and forth. And so here's the same thing. It's an H-bridge. And let's look at that. Saved it, and we can look at it here. And again, you see there are your two transistors, NP, 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 NP. Here is your load, that forms your H. Now, then they have a Hall effect there to detect the north facing, a Hall effect here that detects south facing. And that will do your bipolar commutation. And I will say I built this circuit, and it was just, like a paint by numbers. Even now, I know conceptually, like they're getting the bias to the base correct, and I guess there's like voltage dividers. To be honest though, I still don't know why they chose the specific resistor values or what exactly they were doing. It was just, okay, this goes in A7, this 470 ohm goes there to the emitter, and it worked. And then here's where they're rectifying the changing magnetic field as it's switching back and forth. Yeah, fortunately for dummies like me, they came up with solid state relays. So we can get rid of every single resistor on here. You just need 1, 2, 3, 4 solid state relays. And if you use, instead of like one north facing, one south detecting Hall effect, if you use what's called a ratiometric Hall effect, I think that's the term, linear ratiometric, something like that, but one that will detect north and south and give different numbers for both, then you can run that through the analog digital converter on your Arduino, and you can do this whole circuit with 1 Hall and 4 solid state relays. But that's not what we're using this for. But it's the exact same thing, is that we want to switch the current back and forth, and this time we're going to use it to get the timing right to transform voltage, just like we were doing tapping out by hand. And we're going to use what's called synchronous rectification. We're going to get rid of this diode so that we don't have to worry about the voltage drop. across the diode, and we'll just get the timing by using our oscilloscope. Channel. Sorry. I'm just so happy I bought the thing. Let's build it now. So we're no longer going to need this, but we're going to need these, and then we're going to need a second one of those, just like this. And I think that's all you need. I haven't built this yet, so this is also a bit new. So that's really the heart of the circuit right there. We'll talk through it in more detail in a moment, but first I've compiled a program I call blink all pins, because it blinks all pins on for a second and a half and then off for a second and a half. And what this allows me to do is to test, okay, is pin 7 all right, is pin 8 all right, are the connections okay, are these set in here right, are any of them fried, is power getting to here? So I guess the first thing is just put this here. We know power's coming into the bus lines. Now take your first switch, put in an LED. Is that working? And then the second switch. All right, if I post like the extended version, there's a problem. And so now what you do is you go back and you see, well, is it getting to there? So now it's slowly starting to take shape. You see we got a positive bus line, and that goes out to there, and then the negative bus line goes out to the other switch. And then likewise, you have the positive bus line going out to that switch, the negative bus line going out to that switch. Now we don't want to put any load across here while the blink program is compiled, because if this set of relays and this set of relays are on at the same time, you have a dead short across your power supply, which even at 1.8 volts would not be nice. And for that reason, we're also going to keep it at 1.8 volts. So why don't I also just write the code for you as we go along, and we'll find out if that works. So what we want to do now is we want to have a capacitor that charges up to 1.8 volts and then charges up to negative 1.8 volts. And if we have that, we should have the rest. So I just opened up the simple blink tutorial, and let's get rid of all that. So let's change this to pin 7, and I guess now you got to declare it, so we declare it up here. And so pin 7 high for a second, off for a second, and then we want to say after that's gone off, pin 8 high, pin 8 low. So let's put in the rest. So there's a code now. We declared pin 7 and pin 8 in their output, and then 7 high, 7 low, 8 high, 8 low. And does it compile? Let's see. Compiling, uploading, and it compiles. So now we need to figure out where you would put a capacitor so that when pin 7 goes high, it charges one way, and when pin 8 goes high, it charges the opposite way. So this is where it always gets a little confusing, but we'll just go step by step. So we put a capacitor in. Here's your positive. When that switch goes high, the positive connects to there, and then we're going to have the negative go out to here, and you see the negative is right next to the positive. Oh no, you got a short. But these two sets of switches are never on at the same time. So right now we'll just put a jumper. Okay, that part works. Now we just need to get it to charge both ways. So to complete it, now we want, when this positive goes high and hits there, we want this negative to go around to there, which you see is on the switch right next to this negative line, which would be a short, but that switch is off. So let's put in a jumper there, and we should have it. Okay, so we've got that set up, and it's doing this. It's charging up to 1.8. and it's charging up to negative 1.8. So there's your bipolar commutation, or your H-bridge. Real easy with solid state relays. Now there's one last part to this, all right? And this is a part that I think I have right, but when I was thinking about it, you know, anywhere you put your inductor, you put it there, it's only gonna hit half either the charge positive or the charge negative. So it's like, oh no, you're back to 2 inductors. But what about put this here, and your inductor goes from there to the bus line. Now the inductor's in place for both the positive swing and when you charge it the other way. So if we go back to our code here, now I've just grayed out the 2-second and 1-second delays just in case you want to keep them for like debugging. So we'll 6,000 microseconds and then shut it off for 140, and charge it the other way for 6,000, then shut it off for 140. So when we turn this on, we should see it ringing. Rub the wizard. And we don't see it ringing. I'm no wizard. Actually, we do see it ringing. Why? What's going on? Okay, it helps to actually compile it. So now we have something. Let's see if it'll just clean it up for us with the auto function. Yeah. Ooh, we're getting there. And you can see it already wants to go because we're at 1.8 volts and the V minimum is 4.8, the V max is 3.7. So now let's dial it in and see how good it is. So just to kind of refresh your memory, the way we want this to work is this will charge up from 1.8 to 3.6 volts, and we'll shut it off there, and then when it discharges we'll shut it off there. Okay, so that's where it would be the timing to not transform voltage. So it starts off there at 0, it does go up to like 3.8 from 1.8. Again, this is a little bit off, but it goes to, you know, like 90% higher, and then you let it swing down to there, and then the same thing, it goes 90% lower, but you don't have the two working together. And I got to put this on an amp meter just for a moment, because what does that mean when that goes to there and then back just about to 0? How much? What's it drawing? Well, you'd want to get both of those right back to 0, but they're close, and so we are drawing 639 microamps, and you're getting that 22 volt swing and then down there. So I don't know if there's anything. I honestly don't know if there's anything you can do with that or not, but it's kind of neat that, you know, this, when that goes back to 0, you know, if it got all the way back to 0, it would read as 0 amps. But instead, we're at 639. Now, when we set it to transform voltage, there's going to be more amp draw, but we're going to be able to transform voltage. All right, well, there it is. That's about the best timing I could find. We're 1.8 volts. It's swinging high 13.2, negative 9.2, and the timing was actually different. All right, I got to just pause for a brief moment here. This is just so weird that I have no idea what in the heck to make of this. And if you look closely, you can see it, can't you? And I saw it with the ferrite as well, and I was just like, let's pretend that isn't there. And I'd like to do that here, but I can't. So first of all, we got one inductor. It's charging up to that voltage. Now it's just ringing randomly. You know, in a moment we'll see how well it does transforming voltage. So I don't care about the magnitude of these. What I care about is the frequency. Now, I've just frozen the wrong button, wrong dial. Frozen the trace here. This is 500 microseconds. So let's get that dialed right in. From there to there is about, what would you say, 480 microseconds? Yeah. Here I just kind of lengthened them out to 5,000, and so now this one's more dramatic, but you can see it just eyeballing it. That's faster than this. So what's the equation for resonant frequency? 1 over 2 pi times the square root of LC. Now you can say, well, these ones have more resistance than that. Resistance doesn't come into the equation for resonant frequency. It's it's only induction and capacitance. Induction, it's the same coil. Capacitance, it's the same cap. So then I thought, well, maybe there's some actual polarity to this cap. That, it's supposed to be a nonpolar cap, but maybe it likes charging one way and doesn't like discharging the other. It's either been conditioned or it's broken or something. So I physically switched it around, and it was the exact same. This one was fast, this one was slow. Whereas if it was asymmetry in the cap, then now this one would be slow and this one would be fast. So that's not it. I'm going to do one last thing, which is I'm going to switch these two to here and these two to here. And if these reverse, then it has something to do with the switches that I don't understand. Okay, I switched places for those solid state relays. Exact same thing. This leg is faster than this leg. There's only one other thing to try. This comes out here and goes here. This one comes out here and goes here. And does it reverse? It would still make no sense, but whew. And again, this time this one's got a big voltage swing and this one's small. The other time this one was small voltage swing, this one big. But again, this one was fast, this one was slow. This is horrible. In a good way. But I mean, I should have just left this as, hey kids, it's a cool way to transform voltage. Now I'm left, being the beanie propeller guy. So, I mean, to be honest, this is why I keep doing this stuff. What in the heck is that? Okay, finally. So now I got it figured out. And I was like ready to pull my hair out. And I switched out the relays. I found some right out of the bag, some Comus AC 37s. Those are 60 volt AC relays. So positive 30, negative 30 is what they can do. The problem was that I was looking at it on the oscilloscope, and you have to remember the negative of the oscilloscope is grounded. So you had an earth ground here. That's why it behaved differently when it was positive to the earth ground versus negative. And that's why the oscilloscope is screwing things up. That's why, it was like this thing should transform voltage like a bat out of hell. And it's just topped off there. So what I've done now is I've taken this, the Comus AC 37s, I put it out to a bridge relay. Out to here, I put a meter on there. And I've turned the voltage down to 1.5 volts. We're currently sitting at 0.6. Turn it on. And we are at 65. It's trying to go higher, 67 volts. These are 60 volt relays. So it's also bleeding across the relays there. And we're at 1.5 volts for input. So now it's back to being cool. Now, if you had 1,000 volt switches, you could take that 1.5 volts and you could take it up to a spark gap at 1,000 volts. Whew. So even at 1.2 volts, we're at 61.9, 62, and these can only handle 60 volts. It's bleeding through the relays. So you talk about a jewel thief. That's not a bad one, huh? So it's like the power grid goes out and just have a 1.5 volt battery. Say, if only we could get 120 volts, we could restart the power grid. Let me show you this transformer. So I'm being silly, but I'm happy that I finally figured this out. And now I know also the other one would transform voltage just as well from, at least 50-fold down to 1 volt. It starts getting down below, well, eventually it transforms voltage at least 50, 60-fold. in any event, thanks for coming along, and stay healthy, keep smiling. Talk to you again later. Bye-bye. Not too shabby.